All right, team, settle in. Welcome to your weather intelligence briefing. Look, what we're going to cover in the next few minutes is absolutely critical for our operations on the ground. We need to break down the science behind severe weather, because that's how we stay one step ahead. You see, when you look up at a storm, it's not just rain and clouds, is it? It's the result of a massive, and I mean massive, battle happening up there in the atmosphere. Figuring out who's fighting and why, well, that's the key. That's our first most important step to keeping our communities safe. Okay, here's the game plan. We'll cover the mission briefing, look at the atmosphere's building blocks, and then dive into what happens when those air masses collide. From there, we'll see how that turns clouds into a crisis, and finally, our early warning advantage. Let's get to it. All right, first up, the atmosphere's building blocks. So what exactly are air masses? So when we say air mass, I don't want you thinking about some little patch of air. No way. We're talking about a huge body of air, literally thousands of kilometers across. It's like this giant bubble where the temperature and the humidity are pretty much uniform all the way through. You could almost say each one has its own personality. So how does an air mass get its identity? Well, think of it like a giant sponge. It forms over a big, uniform area. We call that a source region. And it just sits there. It sits and soaks up the temperature and the moisture from the ground or water below it. So if it's sitting over a warm ocean, bam, it becomes warm and moist. If it's parked over a cold, dry desert, you guessed it, it becomes cold and dry. And that really breaks it down into two main types. If it forms over a continent, we call it continental, and that means it's dry. If it forms over the water, like an ocean, we call it maritime, and that means it's moist. Simple as that. Land is dry, water is wet. So when you put those two things together, moisture and temperature, you get these classifications. They're like little codes that give us a quick intel profile. You might hear maritime tropical, or MT for short. That tells you right away it's moist and it's warm. Or maybe continental polar, CP, that's going to be cold and dry. Knowing these codes is like a shortcut. It tells us exactly what we're up against. Okay, now we're getting to the really important part. See, the most dramatic, most dangerous weather, it doesn't usually happen inside one of these uniform air masses. No, it happens right on the edge. It happens at the boundary where these massive things collide. So you have to ask, right? What happens when these atmospheric titans actually meet? What happens is you get what's called a front, and that's exactly what it sounds like, a battle line. It's the boundary where these two different types of air clash, and they do not like to mix. You know, it's like when you pour oil into water, or even hot and cold water. They don't just blend instantly. They fight it out first. Well, this is that same idea, but on a truly colossal atmospheric scale. Okay, take a look at this diagram of a cold front. This is key. Cold air is dense, right? It's heavy. So when it moves in, it doesn't just mix with the warm air in front of it. Instead, it acts like a snowplow, like a wedge. It shoves its way underneath the warmer, lighter air and forces it violently straight up. And that rapid upward motion, that is the trigger. That's the engine for severe weather. Remember this. That lift is what kicks everything off. It's the spark that lights the fuse. So now we see how this goes from just clouds to a full-blown crisis. Let's talk about the impact of these frontal systems. Remember that upward motion we were just talking about? Well, that's what creates a thunderstorm, plain and simple. As all that warm, moist air gets shot upwards, it cools, it condenses, and it forms these enormous, towering clouds. And that's where you get the heavy rain, the lightning, the whole dangerous package. And to really see the danger here, let's zoom in on a specific case study, an urban intensity event that happened in northern Metro Manila. 132.2 millimeters. Now that number might not mean much on its own, but listen to this. In just a few hours, a single storm dumped that much rain. To put that into perspective for you, that's the kind of rainfall you'd expect from a major typhoon, but it all came down in a tiny fraction of the time. And that is the critical danger here. It's not just how much rain falls, it's how fast it falls, the intensity. These short, incredibly violent downpours, they just overwhelm drainage systems. They can't handle it. And that leads to flash floods that can pop up with almost zero warning. Okay, so that's the threat. But this is where we get our advantage. This is how we can turn all of this science into real, on-the-ground action. This is really the so what of this entire briefing. This isn't just a science lesson. Because when we know the science behind the storm, That's when we can build the tools that actually save lives. It's that direct.
And a fantastic real-world example of this is Project NOAA. It takes this exact weather science and turns it into a concrete, actionable program for disaster risk reduction.
So, how does it work? It's pretty brilliant, actually. First, they do hazard mapping. They figure out exactly which areas are the most vulnerable. Step 2, they use a network of over 1,000 automated sensors to get real-time data. And step 3, and this is the absolute game changer, all that intelligence gives communities a crucial 6-hour lead time to prepare. And what this does is it completely changes the mission goal. We stop being reactive, just cleaning up after a disaster. Instead, we become proactive. We can use that data to trigger life-saving evacuations and get people to safety before the worst of it even hits. And that, right there, is the power of this. We're turning weather intelligence into real community action. So, look, we have the intelligence. We have the tools. The only question left is, are we ready to act? That's all for now.